In section 3.8, we will talk about implicit differentiation. Implicit differentiation is when we take the derivative of a variable where the term that we're taking the derivative of and the input variable are different. So what is the input variable? So the input variable is what we take the derivative with respect to. Okay, so in this case, we're taking the derivative with respect to x. Now, the term we're taking the derivative of is x cubed, so the input variable and the term are the same, so we don't need the chain rule. So this just becomes 3 comes to the front, subtract 1. That's our power rule of derivatives. That gives you a 3x squared. Now, in the second example, the input variable is x. We're taking the derivative with respect to x, and the term is y cubed. When this happens, when we take the derivative with respect to x of a different variable, so the input variable and the term are different, then we do apply the power rule of derivatives. So 3 comes down, we have 3y squared, but we do need the chain rule, and we have a dy dx left over. Okay, well, once again, because we're taking the derivative with respect to x of y cubed. Whenever the input variable and the term are different, we're always going to get a dy dx. Okay, here's another example. Let's say we take the derivative with respect to t of 4t to the fifth. So the input variable is t and the term is t to the fifth. They match, so we don't need the chain rule. 5 times 4 is 20, subtract 1, we get 20t to the fourth. But if we take the derivative with respect to t of 4s to the fifth, where the input variable and the term are different, then we still do 5 times 4 is 20s to the fourth, but we have ds dt. Remember in the previous section when we take the derivative with respect to x of like a u, for example, let's say it's u to the second, then the 2 came down, we have 2u, but then we always had a u prime left over. And u prime, that's the same thing as saying du dx. So the thing to remember for this section is anytime the input variable and the term are different, we're going to have this ds dt or dy dx at the end. So implicit differentiation, here are the steps, and I'll go through these steps with you as we do an example. So we want to use implicit differentiation to determine dy dx given x squared plus y squared equals to -4. Okay, so let's take a look at step 1. Step 1, we differentiate both sides of the equation with respect to x. So we're going to take the derivative with respect to x, so d dx, of both sides, meaning every single term. So we take the d dx of x squared, d dx of y squared, d dx of -4. Now, in each case, we are going to apply our rules of derivatives. So these would be the power rule of derivatives, where the 2 comes down becomes 2x. Here, the 2 comes down becomes 2y, but when the input variable and the term are different, we have a dy dx left over. Okay, so that's step 1. And then on the right side, the derivative of any constant is 0, so we can ignore that. Now, over here, we apply the rules of differentiation as we did, and then we'll have a dy dx. We isolate all the terms with dy dx on one side. This is a more simple example, so we only have one dy dx, but you want to get this term on one side and everything else on the other side. And then we solve for dy dx. So we move the 2x to the other side. We just want to get the dy dx by itself. We divide both sides by 2y, and then this will give us dy dx equals to -x over y since the 2's cross out. So remember, dy dx is the same thing as the derivative. Dy dx is same thing as y prime. And we're trying to find the derivative of y with respect to x. Now, one thing we could have done is we could have solved for y, but that would have made a very complicated equation to take the derivative of. So whenever we have x and y on the same side, especially with exponents or other terms, implicit differentiation is often easier in finding the dy dx. Okay, let's take another example. We want to find the slope of the tangent line. So slope of the tangent line, guess what? That is our derivative. So this is the same thing as dy dx. So we want to find slope of the tangent line to this curve at the point 3, -2. So whenever we have x and y on the same side, especially when they're exponents or they're multiple y's, the best way to do this is to take implicit differentiation. For implicit differentiation, we are going to be taking the derivative with respect to x of all the terms. So ddx of x squared, ddx of 3xy, ddx of 2y cubed, and the ddx of 43. Okay, now let's go through each term. Here, the input term and the input and the term are the same, x and x. So that's just going to be 2x. Oh, I'm jumping ahead, I'm sorry. So this here will give me 2x. I'll keep that in mind. Now, I see that here we have a product rule because we have 3 times x times y. And whenever we have the product rule, we need to account for that. So on the side, I'm going to set up the product rule. I'm going to call the first part of it 3x, that's equal to term A, and the second part term B. Now, if I want to take the derivative, so A is 3x, and its derivative is 3. Now, B is y. If I take B prime, what I'm doing is I'm taking the derivative of y with respect to x. So this is like y to the first, so the 1 comes down, all we have is a 1. And then the y goes away because we have y, we take away y. But anytime the input and the term are different, we have a dy dx left over. So what we're going to have is 1 times dy dx, which is just going to be your b prime. Okay, and this says y prime for some reason. I apologize. It should just be a y. So our b term is y, and its derivative is going to be, I'm sorry, it's y to the first. So the 1 comes down, and then the y goes away, but we have a dy dx because, again, input is x, variable is y. All right, so now I have everything I need for the product rule. So let me actually write this a little bit below. So once again, I have ddx of y, and that's going to be 1 times dy dx. Okay, the product rule is going to be b times a prime plus a times b prime. So our b is y, our a prime is 3, our a is 3x, and our b prime is dy dx. Once you have everything here, all we do is plug it in. So now I think we can take the derivative of all these terms. So for x squared, the derivative will be 2x. Now notice we have a minus sign, and then this derivative here, this whole thing, it came out to be multiple terms. So we have to put those in parentheses. Anytime you have multiple terms, make sure you put those in parentheses. So this comes out to be 3y, y times 3 is 3y, plus 3x times dy dx. Let's make that a little more clear. And then here we have 3 times 2 is 6y squared. But again, the input is x, the term is y. So we have a dy dx. All right, let's keep going. Next thing we're going to do is we're going to distribute that negative. So we have a negative 3y, a negative 3x dy dx. I don't know why I keep putting dx dy. I'm sorry. It should be dy dx. And then you have minus 6y squared times dy dx is equal to 0. Now the next step is we have 2 different terms that have a dy dx. So everything else, so we're going to keep this term and this term here because they have a dy dx. All the other terms go to the right. So what we're going to do is we're going to subtract a 2x and we're going to add a 3y. And these two we're going to keep here because they have a dy dx. So the other 2 terms, they go to the right. Okay, so now I have a negative 3x dy dx minus 6y squared dy dx equal to negative 2x plus 3y. So once again, what I have is all my dy dx's on one side, and all these other terms went to the right. But now I have to factor out the dy dx. They both have a common factor, so I'm going to factor that out. So I have dy dx, and in the parentheses I have a negative 3x minus 6y squared equal to negative 2x plus 3y. Finally, I want to get my dy dx by itself, so I'm going to divide both sides by negative 3x minus 6y squared, and that'll be my derivative. But I'm not quite done because the problem says to find the derivative at the point 3 comma negative 2. So I'm going to replace the x's with 3 and the y's with negative 2. So so instead of negative 2x, I have negative 2 times 3. Instead of 3y, I have 3 times negative 2. Same thing on the denominator, replace the x with 3, y with negative 2, and that comes out to be 4 over 11. So this was a very complicated problem because there were multiple things that were happening. One is we had the product rule, which I set up on the side. And then we ended up getting 2 dy dx's. So keep those terms, so this term and this term, keep them on one side, move everything else over to the right, and then factor out the dy dx and divide from there. And then lastly, because we're given a specific point, we replace the x and y with those points to get the slope of the tangent line, which is also the derivative. Now you probably will have questions on this, and just again, if you don't understand this, it's okay. Just come to class prepared with those questions. All right, next one. So it also looks kind of complicated, right? So we want to find dy dx first. So I want to take the derivative with respect to x of all the terms. So 1, 2, 3, 4. I take them of all 4 terms. Then I notice that I have a product rule. I have 9x to the 51st times y. So if I want to take the derivative of this, I'm going to say this first term is a and the second term is b. So a is 9x to the 51st. A prime should be pretty straightforward. It's just a power rule of derivatives. 51 times 9 is 459, and then we got x to the 50th because we subtract 1. Now b is y. So once again, if I take the derivative with respect to x of y, the input and the term are different. So this is like y to the first, so the 1 comes down and the y goes away, but then we have the dy dx. We always have that when the input term and the term are different. Okay, so your b prime is going to be 1 dy dx or just dy dx. So now I can take the product rule and say that this is going to be b times a prime plus a times b prime. My b is y. My a prime is 459x to the 50th. I got the plus sign. And then my a is 9x to the 51st. And my b prime is dy dx. So that's this whole thing is just this middle part, just that derivative right there. All right, okay, now I can start taking the power rule of derivatives. So here I have 3 times 34, that's 102, and I subtract 1, that's x squared. Now this middle part, I already calculated that. That's going to be this whole thing right here. So I put that in parentheses. Anytime there's multiple terms, always put those in parentheses. And then here, the 8 comes down, so we have 8y to the 7th. And the input and the term are different, so we have a dy dx. I take out the parentheses, there's no negative, so there's no need to distribute anything. And now all the terms with the dy dx, I'm going to keep on one side, and these other terms, I'm going to move to the other side. So I subtract those, and on the left side, I'm left with a 9x to the 51st plus 8y to the 7th. But because they have a common factor of dy dx, I can factor that out, just like with the last example. So both of these terms have a common factor. I factor it out. And then lastly, I divide both sides by the 9x to the 51st plus 8y to the 7th to get that dy dx by itself. And if I do that, my derivative comes out to be negative 102x squared minus 459x to the 50th y. All of that divided by 9x to the 51st plus 8y to the 7th. But I'm not done because I still want to find the equation of the tangent line at the point 1, 1. So my x value is 1 and my y value is 1. So remember, this is the derivative. Okay, but we want the derivative at a specific point. So if I replace the x and y both with 1 and just plug this into decimals or any kind of calculator, we're going to get the slope to be negative 33. So once again, think about this, come to class with questions. Oh, I'm sorry, we want the equation of the tangent line. So now we're going to plug in the slope to y equals to mx plus b. The slope is negative 33. Replace the x and y with the point 1, 1, and we get b to be 34. So that's my equation of the line.